Thank you so much for joining this lesson. We shall be discussing the color joint pretrial examination 2025 physics paper 1, and we shall discuss the full paper. So I request you to stay tuned for the next 1 hour or so that we may check what was evaluated in this paper. Otherwise, thank you so much for tuning in. Remember to subscribe, remember to share so that you may invite a friend. Before we start the paper, let me bring you on board our programs, whereby we're going to have a very serious program on August, over the August holiday. So we invite all the secondary school students to register with us. Our line is 0704 15 3366. Please reach out for more information about the same. We shall be handling the sciences, mathematics, and the languages. So we have a very serious lineup of teachers who are going to help you over the holiday. I encourage all the candidates to roll out. Please enroll to our programs and get the best from the best. Have you bought your airtime? Have you purchased your airtime for all your networks? Safaricom, Airtel, Telcom? Just go to your M-Pesa menu. Lipa na M-Pesa option. The pay bill number is 737356. Then now the account number is the phone number that you're purchasing the airtime for. Be it Safaricom, Telcom, Airtel. Just enter the phone number as the account number. Remember, you can even purchase for a friend using the same pay bill, but now the account number is that number of the friend that you're purchasing the airtime for. Then after you complete the transaction, you shall receive the airtime instantly. Try our method and you shall appreciate. Thank you. Thank you so much. Number 1, now on the physics paper. A micrometer screw gauge is used to measure the diameter of a copper wire. The reading with the wire in position is shown in diagram 1. Then the wire is removed and the jaws of the micrometer are closed. The new reading is shown in diagram 2. So we have two diagrams in this case. Diagram 1 is showing the reading when the wire has been fixed in the jaws of the micrometer screw gauge, and we can get that reading. Then later we are having a diagram 2 whereby the wire has now been removed from the jaws, and what is happening is that when the jaws are closed, now there is a certain reading, and this diagram has been drawn for us. That means diagram 2 is going to guide us to identify the zero error in this instrument. So we first get the reading with a zero error. Then now that the zero error has been identified, we use it to get the actual reading. So what are we seeing from diagram 1? We read the diameter there. So the diameter is from 0, we have a 0.5, 1, 1.5, 2.5. So we have a 2.50. That is the sleeve scale reading. Then on the thimble scale, what are we having? The axis of the sleeve scale is coinciding with the ninth division here. Not yet a 10th, so it is 9. So we take 9 and we multiply by the least count, 0.01. This gives us 0.09. So from the thimble scale, we are having 0.09. So we shall add 0.09 and 2.5. This will give us 2.59 millimeters. Remember, readings from a micrometer screw gauge are in millimeters. Then now in diagram 2, we shall identify the zero error. When the jaws are closed and there is no instrument, there is no object, then what is the diagram indicating? On the sleeve scale, we are having a 0.00, but on the thimble scale, what are we able to read? This is a 14th mark. That is the 14th mark, where this axis is coinciding with the thimble scale. 14th mark means 14 now should be multiplied by the least count, 0.01, and this shall give us 0.14. So we have a positive error of 0.14. That means now the reading that we obtained from diagram 1 is together with a positive error of 0.14. In other words, when there is no object between the jaws, there is a reading of 0.14. So after taking the reading, we should subtract the zero error, which is positive. So actual diameter of the wire, actual diameter of the wire shall be 2.59 minus 0.14. We are subtracting. This is going to give us 542. So the final answer is 2.45 millimeters. That is the thickness of the wire. Yeah, thickness of the copper wire which was used. And I hope we are together in that. Ladies and gentlemen, remember to subscribe to this platform. Remember to share the link with a friend. Please invite a classmate, invite a friend, regardless of the school that they come from. Let's grow together in Shifting Grades Online School. Remember also about the holiday program so that you may invite somebody. We have reasonable charges, and I am sure people are going to reap a lot from our program. A vehicle is moving at a speed of 5 meters per second on a flat level road. The speed is then increased to 20 meters per second. State what happens to the friction force between the vehicle and the road during the change. So when you change the velocity or the speed from 5 meters per second, that is acceleration now, what happens to the friction? The friction remains the same. No change in the friction. No change in the friction. Because changing acceleration or changing the speed is not among the factors that affect friction. It is not among the factors that affect friction. It is not. Because friction will be affected by nature of surface or the force which is pressing the surface. That is the normal. And we will talk about the weight of the object itself. So as long as the weight of the object has not increased, then, and the roughness of the road has not been changed, or the course of the tires of this vehicle has not changed, then friction is not being affected by speed. State what happens to the friction force between the car and the air in question 2 above. Now there is a different friction here, which is called the viscous drag. And viscous drag shall increase. The viscous drag, this is friction due to air, is increased. So the faster you run, it's increased. The faster you run, the greater the air friction that you're going to receive. But the normal friction due to the surface, it shall not. We are advised in number 4 to sketch a displacement time graph for a body projected vertically upwards. Remember, when you project a body vertically upwards until it comes to the same position where the projection began, the final displacement is usually 0 because it comes back to where it began its journey. Therefore, such a graph, let me just help you sketch it. We're going to come up with a sketch of this graph with the time, of course. So this time in seconds, and displacement in meters. Displacement in meters. So we shall have the object moving upwards, then later downwards. So that's how we shall have the motion. The displacement at the end of the day shall get back to 0. We can look at number 5 now. A rubber band is stretched by 2.0 centimeters when a force of 4.0 Newton is applied at one end. In terms of molecules, explain what happens to the rubber band. This is during stretching. What makes it stretch? This is due to increase in the intermolecular distances. So intermolecular distances are increased. Intermolecular distances increase. Intermolecular distances increase. Determine the weight of an object that would cause an extension of 5 centimeters when attached to the end of the same spring. So a rubber band is being stretched. Same spring or same rubber band. I think it's a rubber band. Same rubber band. That way. So a rubber band is stretching by 2 when a force of 4 is applied. What about the force that would cause an extension of 5 centimeters? So because it is the same spring, let's talk about a force being given by spring constant times extension, meaning that spring constant can be given by force out of extension. So a force of 4 out of an extension of 2 centimeters can be converted to SI units. That will be 0.02. So the spring constant shall be 200 newtons per meter. Newtons per meter. So with the spring constant now, I want you to know that as long as the spring has not exceeded elastic limit, it shall obey the Hooke's law and it shall have the spring constant remaining the same. Therefore, spring constant and extension are provided in part B. What shall be the force? Force is given by KE. If force is given by KE, then the force that we need shall be given by spring constant times an extension of 0.05. I have to change it to SI units. So when I multiply this by 0.05, I'm getting 10 newtons. So it is a force of 10 newtons that is required now to cause the extension of 5 centimeters. That is what you're supposed to understand. At number 6, pure ice can be converted to water without change in temperature. Without change in temperature. That is a change in state of matter. State, another factor that remains constant. When a substance is being heated until it changes from one state to another, we say that this one happens at a constant temperature. That is one factor which is constant. But now, there are other factors which also remain constant, and that is pressure, the pressure at which this is happening, and also the mass being converted. The mass being converted should also remain constant. The mass of the ice. The mass of the ice is supposed to remain constant. Yeah, that way. Explain how possible it is to skate on ice. How is it possible to skate on ice? So the skater, it's good for you to know that the skater exerts, the skater is going to exert some pressure on the ice. On the ice, melting it. So it is going to melt on the upper part where the pressure is exactly being imparted. Now, if that is where the pressure is being exerted, then a water film or a thin water film, is created due to the melting, enabling the skidding or enabling the skater to slide. Yeah. So the skating is facilitated by the water film, which is generated by the melting of the ice due to the pressure. So the first statement should involve the pressure which the skater is going to exert on the ice surface. Then at that surface, some melting will happen, a water film created, hence sliding is made possible. The figure below shows a uniform-meter rule, number 8 now, of weight 1.0 Newton balanced by a balloon containing hydrogen hung at the 0 centimeter mark. The pivot is placed at 80 centimeter mark, sorry. We have the balloon there. We have the meter roll with its own weight. The balloon and its content weigh 0.5. Determine the upthrust on the balloon. So we're supposed now to understand what is happening here. This is on a moments of a force. We're supposed to understand that the balloon and its content are having their weight acting downwards. Then upthrust is always going up. Upthrust force will go up. Something else that you're supposed to know is that there is the weight of this meter rule, which is 1 Newton, is acting downwards. So now we can talk about, the weight here is 0.5. So we can talk about the principle of moments, which states that the sum of clockwise moments about a point is usually equal to the sum of anti-clockwise moments about the same point, given that the system is in equilibrium. So this system is now in equilibrium, and we can apply the forces that are causing clockwise moments is the upthrust only. So the upthrust, which is unknown, and it is acting from the 0 centimeter mark all the way to the 80 centimeter mark, is the one causing clockwise moment. Because it's going upwards, that means it shall cause a clockwise moment. So the distance is 0.8 multiplied by force, a non-upthrust. They are causing clockwise moment. This is equal to anti-clockwise moment. The weight of this meter rule, it's acting downward, so it shall cause anti-clockwise moment. And also the weight of the fabric of this balloon is also going downwards, so it shall cause anti-clockwise moment. So for the balloon, it is 0.8, the distance, times the weight of 0.5, plus 1.0 weight of the meter rule times a distance of from the weight of this meter rule shall be acting downwards through the center, and that is through the 50 centimeter mark. Therefore, we have 30 centimeters from where the weight is acting to where the pivot is, and that should be 30 centimeters, making it 0.3 meters. Yes, so we shall have 0.4 plus 0.3 equals to 0.8 upthrust. So we talk of now 0.8 upthrust equals to 0.7. And now to remain with the upthrust, we shall divide 0.7 by 0.8, and the upthrust is concluded to be 0.875 Newton. So that is the upthrust, the amount of upthrust which is acting on this particular balloon. A very good question. This one has brought together the concept of floating and sinking, and also the concept of the turning effect of a force. Very good. You can comment to our videos. Let's know where you are learning from. Let's know whether you're getting us clear. Say hi to your physics teacher as we continue learning together. Now at number 9, a car negotiating a corner at a constant speed is said to have a change in momentum. Explain this observation. Explain this observation. At a constant speed, mark that term because there is another word that we're going to involve here. It is said to have a change in momentum. So the change in momentum is due to the change in the direction. As long as it is negotiating a corner, then it shall have a change in direction. So the change in direction, the change in direction leads to a difference or a change in velocity of the body or of the car, though the speed remains the same. So the speed is a constant, it has not changed, but that same speed being focused on a different direction now becomes a different velocity. Since momentum is the product of mass and velocity, it also changes. So because momentum varying with velocity, momentum varies with velocity, then it can't remain the same when velocity has changed. So the argument here is due to the change in direction, which automatically makes the velocity to be different. After the velocity has become different, ladies and gentlemen, momentum, which is a variable affected by velocity, should inevitably also change. The figure below shows samples of equal quantities of same liquid A and B being heated through a well-lagged copper rod of non-uniform cross-section area. A thermometer is placed in each sample after some time. If the rod is being heated at the middle, it is being heated at the middle, so the flame or the heat that you're seeing there is placed at the middle. State and explain which of the thermometers records a higher temperature. Which of the thermometer records a higher temperature? The thermometer at A. The thermometer at liquid A shall record a higher temperature. I'll explain this. This is because conduction or conductivity increases conductivity this time around, it's of it. It's good to have it clear. Increases with the thickness of the conductor. The thickness of the conductor. This is from heat transfer. Those who took one work very serious know what we are saying. The conductivity of heat increases with thickness of the conductor. Thickness can also be used as cross-section area or the diameter. Yeah. In a thicker rod, in a thick or in the thick side of the rod, there are more free electrons per unit length than in the side of thin cross-section area or thin, not thick. The side where the rod is thin, can just say that. Remember, it is the presence of free electrons that facilitates the transfer of heat. So the thicker a rod is, the more the number of free electrons, and hence the better the conductivity. When it is thin, it has fewer free electrons and hence slower conduction. So that is what happened in this question. At number 11 now, a metal weighs 1.0 in air and 0.8 when totally immersed in water. Calculate part 1, the volume of water it displaces. It is good for you people to know that there is something that we call upthrust. Upthrust is usually equal to weight of liquid or fluid displaced. Upthrust equals to weight the fluid or liquid displaced. So in this case, there is an upthrust being experienced. There is an upthrust being experienced. This upthrust is equal to, if the real weight is 1.0, that is the weight in air, 1.0 Newton, but when immersed in water, it weighs 0.8. 0.8 becomes the apparent weight. Therefore, it means that upthrust shall be given by weight, that is the real weight minus apparent weight. So upthrust shall be 1.0 minus 0.8, giving us 0.2 Newton. So we have an upthrust of 0.2 Newton. This upthrust is equivalent to the weight of water displaced. So we can also get the volume of water displaced. So weight of water displaced is equal to 0.2. Weight of water displaced is 0.2. How do we get weight? Weight is given by mass times gravity. How do we get mass? Volume times density equals to mass. So weight will be, instead of mass, volume times density, then times gravity. So volume times density replaces mass, because according to measurement, mass is given by volume times density. So a known volume times density of water times G. I hope we are together in that. This means we can remain with volume by dividing through 0.2 divided by 10,000. This shall give us exactly 2.0 times 10 to the power of -5 meters cubed. I've written it in standard form. Yeah, so that is how you're supposed to move through such a question. Look at the second part of this question. We are told to find the density of the cube. The density of the cube. Remember, this density is weighing 1.0. That means we can get its mass. Mass of this cube equals to 0.1 kg. Yeah, we have to take, for us to get the mass, we take weight divided by g. And the value of g is approximated to be 10 on the Earth's surface. Therefore, mass of the cube, 0.1 kilograms. Then volume of the cube equals to 2.0 times 10 power -5 meters cubed. Remember up there, we calculated the volume of water displaced. Volume of water displaced is equal to volume of the cube. Because it is the cube which is displacing the water, then they have the same volume. You should recall from one work, displacement method of determining volume of irregular objects. When an object is placed where a liquid is, then the liquid gets displaced. We usually say that the volume of the displaced liquid is equal to the volume of the solid which has been immersed. So if it is the cube that displaced the water above, then the cube is also having the same volume. Now with this, we can say that density is given by mass over volume. So mass out of volume. Then we compute this from your calculator very fast. You should be able to get 5,000 kilograms per meter cubed. 5,000 kilograms per meter cubed. That is the density. I have a lot of hope that you guys are learning and getting something from our platform. Remember, ladies and gentlemen, to subscribe. Remember to also invite a friend to this broadcast. Consultation line remains 0704 15 33 66. So kindly remember to contact us for more programs. Now it's number 12. The figure below shows a manometer used to measure the pressure differences between the air inside a plastic container and the atmosphere outside. We have a platform here whose area is 0.1 meters squared, sorry. Then a force is exerted there on a flexible plastic container, which is having some air. So when that is pressed, remember water has to be pushed down on this limb and of course up on the other one. Calculate the force F exerted on the container. Calculate the force F exerted on the container. So this manometer is containing water. That is something we're supposed to know. So with water, then we can calculate the pressure difference. What is the pressure difference, or what is the height which has been pushed up courtesy of this force? That is from 20 centimeters all the way to 80. And that way, we are getting 20 centimeters. So H here is 60 centimeters. We have a height of 60 centimeters there. Therefore, according to the principles of pressure, we know that pressure in liquids at the same level is equal. Therefore, the pressure at this point now, pressure due to water is equal to pressure due to the force. Pressure due to water is equal to pressure due to air. So, pressure due to the water shall be given by H rho g, while pressure due to the air is an exertion of force on some area. So it will be force over area. They are the same. Pressure according to the force shall be F over A, and pressure according to the water column, H rho G. This is what I'm equating now. The two pressures are the same. So if that is so, then the height is 60, 0.6, times density of water, 1,000, times G, 10. This is equal to a force, which is unknown, divided by area, 0.1, according to the platform there. Yeah, 0.1. So we can get our F by multiplying 0.6 by 1,000. This one is also multiplied by 10, that is G, then times 0.1, because we have to multiply both sides by 0.1 by also 0.1 to remain with F. So when that is done, we shall remain with exactly 600 newtons. 600 newtons. So that is the value of the force which has been applied at that position. Number 13. One end of a matchstick is rubbed with soap and placed gently on the surface of water in a basin. The matchstick is observed to move in one direction. So we have the soaped end of the matchstick. Explain why this happens. This is about a surface tension. Those who have covered from one work very well, they know about the toy boats and the matchstick. So the soap is an impurity in this case, and it's going to dissolve in the water. So when the soap dissolves in water, or we can start by recognizing that it is an impurity. The soap dissolves in water and lowers the surface tension at that point. So now we shall have a difference in surface tension. The side where there is soap, there is lower surface tension. The other side, which is not having some soap, shall have a higher surface tension. So the surface tension on the other side of the stick, which is now greater, holds the stick. The surface tension on the other end, which is now greater. Remember, it has not been lowered like the other part. It is going to pull the stick, the matchstick, towards that direction. Remember, there will be now a movement such that the end without the soap is leading. So the movement shall continue until it stops, until the stick stops. So it continues until it stops, because eventually the soap which dissolves in the water will dissolve and spread until there is an homogeneous soap solution such that the whole mass of water is having soap molecules. That way, surface tension shall balance again and the motion shall stop. So that is what you're supposed to understand. Now there is a section B here. And in this one, we're supposed to be very detailed, very keen. Those who are joining us late, please be reminded of our holiday programs. You can enroll. Kindly reach out through 0704 15 3366. I am going to help you register. and I will help you to get the best from the best. We have a lineup of serious teachers who are going to facilitate us through the sciences, mathematics, and English. So please don't be left out. There is also this mode of purchasing airtime. Those who are using Safaricom lines, Airtel lines, Telcom lines, you can load airtime of any amount from your M-Pesa to the line by going to the M-Pesa Lipa na M-Pesa option, then the pay bill number 737356. Then the account number is the phone number now that you're purchasing the airtime for. The phone number that you're purchasing the airtime for, you enter the phone number as the account number. It can even be the phone number of a friend that you're purchasing the airtime for. Then after that, now you proceed to enter the amount, you complete the transaction, then you shall receive your airtime instantly. Please embrace our approach as we grow together. Now in section 2 or section B, 55 marks. Remember, all the questions in physics are compulsory. Something that you should take very serious. All the questions are compulsory. Proceed now. Determine the time specific latent heat of fusion. Mark the word specific because sometimes you'll be taught to define latent heat of fusion. So when we talk about specific, then this is the amount of heat energy required to change a unit mass. This is the amount of heat energy required to change a unit mass. To change a unit mass of a substance or to change the state. To change the unit mass of a substance from solid to liquid at a constant temperature. Instead of saying at a constant temperature, you can also say to change a unit mass of a substance from solid to liquid without change in temperature. Yeah, without change in temperature. Look at part B of the same question from quantity of heat. In an experiment to determine the power of an electric heater, melting ice was placed in a container with an outlet and the heater placed in the ice as shown below. The melted ice was collected. Other than the current and voltage, state two measurements or two other measurements that would be taken in order to determine the quantity of heat absorbed by the melted ice. In order to determine the quantity of heat absorbed, and that would be time taken for the ice to melt, in this electrical method, time is very key. Something else which is very important is mass of the melted ice. Remember, mass of the melted ice should be taken with reference to the time. So by the time you are observing the time taken, that is the time you should withdraw the beaker containing melted ice so that you may determine the mass. The same time, because you might determine time, then you start delaying the measurement of the mass such that accuracy is tempered with. So for you to ensure that accuracy is sustained, the time should reflect the amount of mass or the mass of the ice which has melted in terms of the water collected. Because if you don't withdraw immediately, you might end up collecting, more water, which is melting due to other factors maybe. If the latent heat of fusion of ice is a LF, show how the measurement taken above can be used to determine the power of the heater. So to determine the power of the heater, we should say that heat energy, heat supplied by the electricity. Now we are having an electric heater. So by the electric heater is equal to heat absorbed by ice to melt the latent heat of fusion. In other words, heat supplied by the heater is given by power times time. And power is VI. Remember, the measurement recorded from above is VI. From the experiment we are talking of, other than current and voltage. So VI times the time taken, that is power times time, that is giving us the heat from the heater. This is equal to mass times latent heat of fusion. And how do we remain with show how the measurements can be used to determine power? We are determining power here. So how do we remain with power? Power is the product of VI. So this is equal to divided by time. Yeah, we divide by time that way. Since power equals to VI, electric power is VI. So that's how we work out such a case. Now at number 3, it is found that the power determined in this experiment is lower than the manufacturer's value indicated on the heater. Explain. The power is differing. The power you calculate in this formula is now going to differ with the power indicated by the manufacturer of this heater. What could be the issue? This is because the machine might be very efficient, but now, according to the experiment, look at the experiment. Some heat might be getting lost to the surrounding. This one is even in a container, and we have not been told that the container is lagged. So most of the heat is being absorbed by the container. That one we didn't account for. So there are heat losses. So all the heat energy, there are heat losses during the experiment. Heat losses during the experiment. These ones can be to the surrounding and also there is heat absorbed by the container. Meaning that hence less power, or hence less power is realized. So you realize some lesser power than the original, not because the machine is having any problems, but because during this experiment there are possible heat losses. There are possible heat losses. Possible heat losses. Yeah. And actually, we can have some other inconsistencies in such an experiment. Sorry to take you back. Let me mention that we can have some other inconsistencies. Inconsistencies like what? In these cases, it's very possible to have maybe the recording of the time and the recording of the mass being inaccurate. That way, we might not get actual figures. So we can have some ordinary inconsistencies during this experiment. An electric heater rated 12 volts, 25 watts is immersed in a well-lugged calorimeter containing 100 grams of a liquid at its boiling point. The cover of the calorimeter has a vent to allow vapor to escape. As the liquid boils, the mass remaining is measured at intervals of 20 seconds. At intervals of 20 seconds. The figure below shows the graph of mass evaporated against time. Mass evaporated. Mark that. Mass evaporated against time. So we have the graph here. Mass evaporated in grams against time. Yeah, against time in seconds. Use the graph to determine the specific latent heat of vaporization of the liquid. We know very well that power times time this one gives electrical energy, which is going to be supplied. And this one is the energy that is going to be used by this liquid to vaporize. If it is the energy that will be used by the liquid to vaporize, then this one should also be equal to mass absorbed by the liquid to vaporize, which is given by mass times latent heat of vaporization. Therefore, you can look at the graph. It's passing through the origin. So on this equation, we cannot add anything else. So let me have this. Let me have this, ladies and gentlemen. Let me have mass times latent heat of vaporization being equal to power times time. Meaning that if I have to remain with mass on this side, then I'll be having power times time divided by latent heat of vaporization. Latent heat of vaporization. Now I have to relate this with what we call the equation of a straight line. Mass has been plotted on the y-axis. Remember, the general equation is mx plus c, whereby this is the value plotted on the y-axis, and that is mass. Then the value plotted on x is time. That is true. But now the coefficient, the value of gradient, which is the coefficient of the quantity on the x-axis, is power out of latent heat of vaporization. The power is already a constant and provided. So you are supposed to know that from this particular graph, I have analyzed the graph according to straight lines. So from this graph, the slope is going to give us power out of LV. So let's get the slope first. Let us get the slope first. So we need to identify some coordinates so that they may help us to get the slope in this case. We just need to identify any fixed coordinates so that we use them to get a slope. Yeah, so we can use, actually we can use any coordinates I can use the coordinate at this point and also the coordinate 0, 0. You should be that wise. You pick the fixed coordinate, which will not help you in interpreting the decimals. So I'm picking a coordinate at 120, 1.0, and another coordinate, 0, 0. So what will be the slope? Change in y, 0 minus 1 out of 0 minus 120. So what shall be this fraction? I take negative 1 over negative 120. So 1 over 120, giving us 0.00. Or let me write it as a fraction, 1 over 120. This is we have grams here, and we have time. So grams per second. Grams per second. 1 over 120 grams per second. That is the slope. That is the slope. So if that is the slope, then we can convert it from grams per second to what we call kilograms per second, so that you work with SI units. So 1 out of 120, 1 out of 120. This can further be divided by 1,000. Yeah, to make them kg. So it is 1 out of 120,000 kilograms per second. Now, this is the slope. If we are having the slope, then we should get to the formula here and say that the slope is representing power over the specific latent heat of vaporization. Therefore, 1 over 120,000 equals to power. The power is known. The power is known and provided as 24 watts. So this is equal to 24 watts out of the latent heat of vaporization. I was trying to avoid decimals at early stages, because when you work with fraction, you move with the accurate values. But when you work with decimal points, you have to round off. So how do we get LV now, the latent heat of vaporization, specific latent heat of vaporization? You cross multiply. So that LV times 1 becomes 24 multiplied by 120,000. So latent heat of vaporization shall be this one. I'm going to multiply by 24. I'm getting 2,880,000 joules per kilogram. Joules per kilogram. So that's how we get the latent heat of vaporization, the liquid. It's a very good question. More so, it is examining on the interpretation of graphs, and learners should be good at that. You're supposed to understand something here. You are supposed to understand something here, but in paper 1 and paper 2, that is the theory examinations, graphical work is usually plotted for you. The graph is plotted. Yours is to interpret. So you should be having very sharp skills of interpreting graphs. Very sharp skills of interpreting graphs. That's the way of learning. So please be in a position to follow through and understand what is happening in such questions. The figure below shows a 200 gram mass, placed on a frictionless surface and attached to a spring, just as you can see. the spring is compressed and released. Given that in part one now, given that the elastic potential energy of the compressed spring is 2.7 times 10 to the power of negative 2 joules, determine the maximum speed with which the block moves after it's released. So once you compress the spring, it possesses what you call elastic potential energy. But once you release that spring, all the energy shall become kinetic and it shall be translated to the object, to the solid, and it shall move with it. So we can see all the elastic potential energy is converted to kinetic energy. That is why the solid will move. The block shall be moving. So this energy is having a value which is 2.7 times 10 to the power of negative 2. This is equal to kinetic energy. And remember, kinetic energy is given by half mv squared. So this is equal to half mass 0.2 kilograms. I'm converting the 200 grams multiplied by a known v squared. Yeah, a known v squared. That means we can now proceed to calculate the value of the velocity involved. We can get v squared first, because for us to get v squared, what do we need? We need 2.7 multiplied by 2, but divided by 0.2. So I'm getting 0.27. This translates to the value of v being the square root of 0.27. And this is going to be exactly 0.5196 meters per second. So this is the velocity the body shall move at. You know, to remain with v squared, to multiply by 2, which is the denominator, then divide by 0.2, which is the numerator on that side. So you should be able to understand the move that I took. Look at part 2 of the same question. Sketch on the axis below the variation of potential energy, kinetic energy, and total energy with the time, given that the spring obeys Hooke's law. If the spring obeys Hooke's law, then we shall have the total energy remaining a constant. Total energy does not change. That is what you're supposed to understand. Remember, we are sketching 3 factors here. So throughout everything, total energy remains the same. Total energy remains a constant throughout this thing. So we have during the compressing, the gravitational energy, not gravitational, but potential. The potential energy during compressing shall decrease from maximum. We use a blue. From maximum, it shall decrease to 0, then rise again. This is now potential energy. But there is another energy that we are calling kinetic energy. The kinetic energy shall start from 0. Remember, when potential energy is maximum, kinetic is 0. And as the gravitational, as the potential, which is the elastic potential, is decreasing, kinetic is going in the opposite direction. It is increasing. Then at maximum, kinetic is the least. So this is kinetic energy. I want to explain the graphs now. The time kinetic energy is maximum, potential energy is minimum. There is a time they are equal at this point, but you should know that when elastic potential is maximum, at the same time, kinetic is minimum. So as the elastic potential energy starts converting, it starts reducing as the same energy becomes kinetic. And that is why kinetic is increasing as elastic potential is decreasing. That way. So that is the graph that is expected in such a case. Look at part B. A man uses an inclined plane. This is one of the simple machines to lift 100 kg load through a vertical height or a vertical distance of 5 meters. The inclined plane makes an angle of 30 with the horizontal. So you can see what is happening there with the horizontal like that. Indicate one force acting on the mass. So one force shall be its own weight, which is acting downwards, or friction, which is acting backwards. Frictional force. Definitely there is a friction force acting against. Is it a frictionless surface? No. The surface is not frictionless. So we have indicated some of the forces. Calculate velocity ratio of the machine. Now, in an inclined plane, velocity ratio is usually given by 1 out of the sine of theta. In this case, theta is the angle of inclination. So 1 over sine 30. This will give us a VR equivalent to 2. That one we are sorted. The other things that we are getting is the mechanical advantage. We are also finding the mechanical advantage of this machine if the efficiency is 80%. We know that efficiency is usually given by mechanical advantage out of velocity ratio multiplied by 100. Therefore, 80 equals to mechanical advantage out of velocity ratio times 100. How do we remain with mechanical advantage? We take 80 by 2 over 100. I'm getting 1.6. Remember, mechanical advantage is a ratio and it does not have units. So mechanical advantage is the ratio of load out of effort. What are we finding here? The effort required to move up the inclined plane at a constant velocity. So mechanical advantage, which is 1.6, should be the load. We are moving 100 kg, which is 1,000 Newton. 1,000 Newton out of a known effort. So we can get the effort, and this is going to be 625 Newton. 625 Newton. That's simple. That's simple. That's simple. So that's how we work out such a question. At Roman 4, we are also finding the work done against friction. What is the work done against friction? So we can check the work output first. Work output, whereby at the end of the day, this load has gone through the vertical height of 5. Therefore, work output equals to the load that we are lifting times the distance that we are taking it through. This is 5,000 joules. Now, this work output, according to the efficiency, it's 80%. So we can say 80% equals to 5,000 joules of energy or joules of work. What about the 20%? This is now what goes to the friction. What about 20% that got lost? So 20 times 5,000 out of 80. This is what now was done against friction. And this is going to be 1,000. I'm getting exactly 1,000. 1,000 joules. Yeah, exactly 1,000 joules. 1,000 joules. So that is it. 1,000 joules. So that is work output. So the work output represents the efficiency, which is 80%. So that is how the question should be interpreted. There is a number 16 here. A student in Color High set up an experiment to study the motion of a trolley, which was accelerating using a ticker timer tape. The timer made 50 dots per second. This one is a very key information. 50 dots per second on the tape. Dots A to E measured 2.5 centimeters apart, and dots E to I measured 4.5 centimeters apart. Using a scale drawing, show the dots as they appeared on the tape. Therefore, we're supposed to use a scale drawing, meaning that we shall not sketch. Instead, we shall use real drawings or real measurements. So if this is the tape, something that we're supposed to ask ourselves is, do you know from A, we're supposed to go to B, C, D until E. So we have 1, 2, 3, 4 spaces, and the total distance is 2.5. So we divide this by 4 spaces, and you discover that the distance in between is 0.6 and a quarter. So we shall use 0.6 centimeters throughout as the spaces. So 0.6 until we cover 2.5. So that is 2.5. And that means this is E. So now we have to make 4 spaces in between. We have to make 4 spaces. That way. We make 4 spaces which are equal using the intervals of 0.6. So now using those intervals, this is B, C, D, E. So we are done there. Then from E all the way to I, from E to I, how many spaces again are there? 1, 2, 3. From E to F, 1, 2, 3. Yeah, there are 3 actually. But you're supposed to know that there is something that was left here. Sorry for that. Yeah, there should be H there. Of course, the alphabetical letters are following one another in that order. Therefore, with that, we are supposed to know that there are 4 other dots. So 4.5 divided by 4 spaces. Let me first place the distance of 4.5. So that we may say this is where I shall be. If that is where I shall be, then we can now, I shall be here. So we can now divide into equal spaces of 1.15 each. 1.15 each. 1, 2, 3, like that. So I'm using my ruler on the screen. That's why I'm able to divide very quickly. And this is going to be F, G, H, I, that way. So this is what the examiner wanted to see now. Just this part. Just that part. That is what the examiner wanted to see. When distances have exactly been measured. Distances have been exactly been measured. Now calculate the velocity of the trolley from A to E. So from A to E, we can first identify the time taken. Remember, there is a what you call frequency here. 50 dots per second means the frequency. So frequency equals to 50 hertz. That means there is what you call periodic time t, the time from one dot to the next, and that shall be the reciprocal of 50. This reciprocal of f gives us periodic time. So from one dot to the next, there is a time interval of 0.02 seconds. With that knowledge, now we can say that velocity shall be distance over time. Distance is 2.5 out of time, which is 0.02 times 4. Times 4, yeah. Times 4, because to move from A to E, how many intervals? 1, 2, 3, 4. So we have 4 intervals. So that is the time taken. When we divide all this, we shall get 31.25. Centimeters per second. This velocity can be expressed as 0.3125 meters per second in SI units. Then from E to I, velocity shall be again distance over time. So distance is 4.5. Time taken 0.02 times 4 intervals. So when you divide this, you shall get 56.25 centimeters per second. This is 0.5625 meters per second in the SI units of velocity. Yeah, the SI unit of velocity. Remember to subscribe, remember to share so that you may invite a friend. Calculate the acceleration of the trolley. Calculate the acceleration of the trolley. So the acceleration of this trolley, remember acceleration is usually final velocity minus initial velocity out of time. So final velocity is 0.5625 minus 0.3125. Then we divide by time. Time shall be 0.02 multiplied by, how do we count the dots during acceleration? How to count the spaces during acceleration is, within the first region, we take half the number of dots, and within the second region, we take half the number of spaces, not dots. Therefore, from the first space, we have 1, 2, 3, 4. So we pick 2. In the second, where there is the final velocity, we have 1, 2, 3, 4. So we pick half of that, which is 2. Then we add. So we are having 4 spaces now for the acceleration. 4 spaces for the acceleration. And so this now shall give us an acceleration which is equal to 0.5625 minus 0.3125. This is 0.25 out of 0.08. This is going to be 3.0 125 meters per second squared. Yeah, meters per second squared. That way. Meters per second squared. So that's how we get acceleration. Now at part B of the same question, still on linear motion. Yeah, still on linear motion. Remember to subscribe. Remember to share with a friend. Just invite somebody to our live broadcast. Just invite somebody to the live broadcast that we're having here. An object is released to fall vertically from a height of 100 meters above the ground. At the same time, another object on the ground is projected vertically upwards with a velocity of 40 meters per second. Calculate the time taken before the objects meet. We have two objects here. We are having 100 meters here on the ground. So one object is on top and it's going to be released. When released, the height covered is given by ut plus half gt squared. Ut plus half gt squared. Then there is another one which is on the ground and is being projected upwards, whereby the height it shall cover is given by ut minus half gt squared. That way. Now, the one being released from top during free fall, because that is free fall, the other one is vertical projection. During free fall, the initial velocity is usually 0. So the height it shall cover is given by half times g times t squared, because initial velocity is already 0. So when we substitute a 0 there, then we will not have a, when we substitute a 0 there, that part shall disappear. So the height moved by the first object, which was released, is 5t squared. That one is sorted. Now, the other one, which is coming from below, the height it shall cover is 40 times unknown t minus half g t squared. So if we simplify this, the second height, this is height 1, height 2 now, 40h minus 5t squared. So something that you're supposed to understand is that now these two different heights, because t is the same, when we take 5t squared and we add 40t minus 5t squared, we're supposed to get the total height of 100 meters. The height 1 for the object which is dropping, and height 2 for the object which is going up, they should add up to 100 meters because they are meeting somewhere after covering different heights, of course. Therefore, now let's have this one combined with this. They disappear. So 40t equals to 100. The value of t can now be obtained. The value of t can be obtained 100 over 40. This gives us 2.5 seconds. 2.5 seconds. So I hope we are in agreement in that. A very good question, which requires a student to be reasoning, student to be having the knowledge on vertical projection, free fall, horizontal projection, or the motions, in other words, just to be conversant with everything. Part 2 now, determine the height from the ground where they met. So we consider now the object which is moving from the ground. The object moving from the ground is the one covering H2. So H2 from the ground is 40 by 2.5 minus 5 by 2.5 squared. So what are we getting here? 40 into 2.5 minus 5 into 2.5 squared. This is going to be 68.75 meters from the ground. Alternatively, we can consider height 1. The first height of the object which is coming from up is 5t squared. So 5t squared. You know, 5 into 2.5 squared is 31.25 meters. But this one covering 31.25 is coming from top. Therefore, from ground now, from ground, we need to take 100 and we subtract 31.25. Automatically, 68.75 meters. So that's how we are supposed to work out such a question. Very interesting question from linear motion. Very interesting question from linear motion. So thank you for being around. We are continuing until we wrap up, until we finish the paper. So please remain around, remain locked in. Subscribe, invite a friend, just share our link. In other words, just share the link so that you may invite a friend to our live lessons. Very interactive. You can comment. Let's know where you are catching us from. Comment. Let's know where you are learning physics from. Let's know whether you are getting something tonight as we proceed to number 17 of this interesting paper. A very good exam, ladies and gentlemen, which we cannot afford to fail to discuss. So we cannot start doing another day for this paper. Let us finish everything and get something tonight. State Newton's second law of motion. State Newton's second law of motion. So the second law of motion, according to Newton, states that the rate of change of linear momentum of a body, let me just write it to save on time. The rate of change of linear momentum, or simply momentum, linear momentum of a body is directly proportional to the resultant force causing the change. Is directly proportional to the resultant force causing it, to the resultant force causing the change. And it takes place in the direction of the force. In the direction of the force. In the direction of the force. That way. Part B. The figure below shows a graph of impulsive force against time for a ball that falls on a cemented surface. Sketch on the same axis a graph for the same ball if it falls on a trampoline or trampoline. So let's first of all know what a trampoline is. Let us know what a trampoline is. Then we are going to sketch the graph. We shall sketch it. So let me take you to what trampoline is. Trampoline meaning. When you talk about trampoline, This one, you know, there is a difference between a cemented floor surface, which is very tough. But now we are talking of another case whereby it shall land on a springy surface, a springboard whereby people can land during acrobats and gymnastic exercises. So during gymnastics, during acrobats, we have people landing on a surface which is called a trampoline. During so that rebounds can be experienced. So in the first case, the ball sharply goes up. The ball sharply goes up. That is the impulsive force. You can see the impulsive force is very high. But now, when we land on a springy surface, we shall have the force being a little bit minimized. So this is how the behavior shall be. A small force, but taking a lot of time. Small force taking a lot of time. Actually, according to the second law, this one is the reason why we have spongy materials like mattresses during high jumps and triple jumps in athletics. So that when the athlete lands, he may take time to reduce from maximum to minimum momentum. Because if momentum changes instantly, like in a cemented surface, there'll be a great impulsive force. But now, when it is a spongy or a springy surface, like the trampoline or the trampoline, then we will have a small force and taking time. Small force coming out, but taking time. So that is what you're supposed to know. In other words, F, which is impulsive time, is given by mv minus mu out of time. The bigger the time taken, the smaller the force. So in a trampoline, we shall have long time taking in the change of momentum from maximum to minimum. Change in momentum shall take a lot of time. If it takes a lot of time, then the impulsive force is going to be very small. That is why injuries are reduced. Look at part C of this. A string of negligible mass has a bucket tied at the end. The string is 60 centimeters long and the bucket has a mass of 45 grams. If the bucket is swung horizontally, making 6 revolutions per minute, calculate part 1, the angular acceleration. We should know that there is something that we call omega, which is the angular velocity. Angular velocity is given by 2 pi f. 2 pi f. Yeah, 2 pi f. Or instead of 2 pi f, it can be omega equals to 2 pi out of t. Yeah, that way. So according to the instructions up here, 60 revolutions are being made in a minute. How many revolutions? 6 revolutions are happening in 1 minute, so in 60 seconds. So we can ask ourselves, in 1 second, how many revolutions will be there? 6 over 60, which is 0.1. 0.1 now becomes the frequency. Frequency is the number of revolutions per unit time. The number of revolutions per unit time. So if in 60 seconds we have 6 revolutions, then in 1 second we shall have 0.1 revolutions. So we have the frequency already. So omega is given by 2 pi f 0.1. So what is going to be the value of omega? 0.6284 radians per second. Radians per second. And we have, now that we have omega, then we know that centripetal acceleration or angular acceleration is given by, when we take the value of r and omega squared, then we shall be talking of a radius of 0.6 times 0.6284, which is our omega squared. This is going to give us 0.2369, since it is acceleration, meters per second squared. So you're supposed to be conversant with the formulae which are used under uniform circular motion. Tension on the string during a horizontal circle, in an horizontal circle, tension is usually equal to the force which is generated, and it will be given by mass multiplied by centripetal acceleration. So the mass is 45, mass of the bucket 45, which is 0.045. We make it as a unit, then we multiply by acceleration 0.2369 that way. So when we carry out this multiplication, we'll be getting 0.0107 newtons. So this will be the tension on the string. Tension on the string. That will be the tension on the string. We have another question here that says, to avoid skidding in a banked rod is a rod which has been raised on one side to increase the angle. The banking angle. One must not exceed critical speed or critical velocity. The first thing is to define critical velocity. This is the maximum speed. This is the maximum speed for a vehicle or for a car or for a body in a circular path beyond which skidding occurs. I hope that statement is well understood. Beyond this particular speed, skidding shall occur. Beyond which skidding occurs. Then now we are almost finishing, ladies and gentlemen. So let's check at the next. State the factors that determine critical speed on a banked road. So we'll state only two: radius of the curve or radius of the path. Radius of the path, the circular path, and something else is size of the banking angle. Size of the banking angle. These are the factors that affect the critical speed. Look at this. Part E. The figure below shows the planet Venus orbiting the sun in a circular orbit at a constant speed. So all the planets, Venus included, move around the sun, in an orbit. Indicate the direction of the constant speed of Venus on the diagram. So we have the direction already shown, which is anti-clockwise. So means that the direction of the linear velocity should be a tangent at that particular point. So in case the centripetal force is withdrawn, Venus will fly off through such a tangent at a linear velocity. at a linear velocity. That is it. Look at F. A bullet of mass, 15 grams, traveling horizontally at a speed of 200 meters per second, bends itself or attaches itself in a block of wood of mass, 1100 grams, suspended from a light, inextensible string so that it can swing freely. Calculate part 1, the velocity of the bullet and the block immediately after collision. According to the law of conservation of linear momentum, we usually say that momentum after collision and momentum before collision is the same. So what is momentum before collision? Momentum is mass times velocity. So for the bullet, mass is 15. We have to take 15 over 1,000, so that it is in SI unit, times 200, plus momentum of the wooden block, which is having a mass of 1100. We also make it as a unit, times the velocity it has, because it was at rest, it has a velocity of 0. This one should give us, after they have attached together, they are embedded together, then the mass shall be, let me get that mass, 15 over 1,000. Then I add 1.1. I'm getting 1.115. That is the combined mass multiplied by the new velocity that they shall move at. So 15 over 1,000. This is 0.015 plus 0.115 times V. How do we remain with V? We divide by 1.115. And the velocity they shall move at together, the velocity they should move at after collision. I want to check whether there's something I'm confirming. No, I didn't multiply by 200, sorry, after this conversion. Yeah, because the velocity was becoming too small. So now the velocity is going to be 2 after dividing through now, 2.691 meters per second. So the two shall move together at a common velocity, and that is it. Then something else that we are advised to calculate is the height through which the block rises. How high shall they move? So they are moving at a kinetic energy, but the time they are occupying the highest height possible, they shall have zero kinetic energy. So the kinetic energy they are having immediately after collision shall be converted to gravitational potential energy at the highest height that they shall manage. So through this, we can say kinetic energy is half mv squared. This will be the same as gravitational potential energy, which is mgh. Through this, because it's the same objects, the masses can cancel out because it is the same mass appearing on both sides. So half times 2.6, sorry, 2.691. This one should be squared. This one should be squared. We get the same as gravity times the unknown h. So let's square this velocity. Then we multiply it by a half. This one should be divided by 10 now to give us a highest height of 0.3620 meters. That is the possible height they shall attain together after collision. Then we have number 18. Yeah, this is the last question now. Number 18 from gas laws. The figure below shows an experiment to verify a certain gas law. Study it and then answer the questions that shall follow. We can see some apparatus here, a source of heat, dry hair, water, a glass tube, thermometer, a Borden gauge. State two measurements that should be taken in order to verify the law. In order to verify the law. So there are instruments here like thermometer, so temperature from the thermometer, and also pressure, because you can see presence of the Borden gauge. Because you can see presence of the Borden gauge, then pressure is inevitable. Then after those measurements, you're taught to explain how the measurements above can be used to verify the law. Okay, first of all, which law is this? Which law are we talking about? So you are supposed to establish the law first. The law that varies or that deals with the variation between temperature and pressure is called the pressure law. So the law in question here is the pressure law. Pressure law. So you're supposed to now carry out an experiment here. So you record initial. Yeah, my pen is almost down, so let me charge it a little bit as we continue learning together. So as we wait for the pen to charge a little bit, I want to bring to your attention again our holiday programs here, whereby, ladies and gentlemen, you are encouraged to enroll to this particular program. It shall be very great. I'm telling you the truth, it shall be bigger than before. Those who have been in our programs can tell. We are going to have a very serious facilitators taking you through the sciences, taking you through mathematics, and also the languages. So we are having a lineup of very serious tutors. Please reach out through 0704 15 3366. You shall get helped in our program. So let's now check how to use the above measurements. You record initial temperature and pressure of the air. So heat it gently, or as heating continues, heat the air, and as you heat, you can you heat the dry air and record temperature with corresponding values of pressure at regular intervals of time. At regular intervals of time. Regular intervals of time. What does this mean? As you continue heating, the time you are recording a temperature value, confirm corresponding pressure at that particular time, so that you may know when pressure becomes this value, what is the temperature? When temperature raises or decreases to this value, what is pressure? Tabulate several values. Tabulate several values. So now develop a table having temperature values and pressure values. And now at this, you plot a graph of temperature against sorry, not temperature. It's pressure against temperature, not the other way around. Pressure, that means pressure is taking the against temperature. So pressure is taking the y-axis, while temperature takes the x-axis. A straight line shows that pressure is directly proportional to temperature. Hence, the pressure law is verified. Hence, the pressure law is verified because a straight line shows that actually through the origin shows that the quantities are directly proportional. And that is the claim according to the pressure law. Part B. What are we told here? The mass of a fabric of a large balloon is 100 kg. The balloon is inflated with 200 meters cubed of helium. The balloon is attached to a cable fixed to the ground as shown. The density of air and helium are given there respectively. Look at the first part of this question. We are taught to calculate the tension on the cable. Therefore, this balloon is going to displace some upthrust like that. And through that, we shall have some tension on the cable. Some tension on the cable. Because, some tension on the cable. That is why actually the upthrust is greater than the weight of the fabric. That is why the balloon is not falling to the ground. There is a tension on the string because the balloon is being lifted upwards by the upthrust. So we shall say that in this case, we will have a upthrust, or the tension will be the difference between the upthrust and the weight. The difference between the upthrust and the weight. Reason being that the upthrust is greater than the weight. That is why there is some tension on the string. Upthrust is greater than the weight. So that difference brings the tension. Therefore, in such a case, we're going to ask ourselves some simple questions like, what is upthrust? Upthrust is the amount of air that is getting displaced. So the balloon has been stretched by 200 meters cubed of helium, which means the balloon itself is having a fabric whose volume is 200 meters cubed, meaning that it shall displace air of equal volume. So upthrust will be given by weight of air displaced. Volume of air is 200. The volume of air is 200. Let's get upthrust on its own first. The upthrust on its own shall be volume of air displaced times the density of air displaced. So for air 1.3, this one should be multiplied by G, which is 10. Yeah, we multiply by 10. Let me carry out that calculation. Volume times density times G. So you discover that now the upthrust is 2600. What about the weight of the fabric? This balloon fabric, the material itself is 100 kg. So can multiply this by 10. Then we add the air inside it, which is helium, occupying 200 at a density of 0.18 times a G of 10. So what is this? 1,000 plus, that is the fabric on its own. Then the helium inside is 360. So you discover this is 1360 newtons, and upthrust is 2600. Therefore, now the tension on the string shall be 2600 minus 1360. So 2600 minus 1360, giving us 1240 newtons. So that is the tension on the string. The tension on the string. So if the weight of the balloon together with fabric, the fabric and the air inside were greater than upthrust, we would have the balloon resting on the ground. But now that it is upthrust that is greater, then there is tension on the string. So this one is calculated. Part C. When an inflated balloon is released to the atmosphere such that it achieves maximum height, it is observed that the balloon stops moving upwards and is seen drifted sideways. Explain this observation. It is observed that the balloon stops moving upward, then it drifts sideways. I just want us to explain using this one. In case we release the balloon, we shall have the balloon displacing some air, that is a upthrust acting on it, and it shall continue until at a certain point whereby upthrust shall equal weight of the balloon. Remember, upthrust is pushing the balloon upwards, and the weight of the balloon together with the air inside are acting downwards. So at that critical point, at that equilibrium where they are equal, the resultant force shall become zero. The upward force and the downward force neutralizes. So the resultant force becomes zero. And so the balloon shall start drifting sideways without going either down or up, simply because the resultant force has become zero. So at the maximum height, we say the upthrust equals the weight of the balloon. The resultant force becomes zero. When the resultant force becomes zero, the balloon hence drifts sideways. The balloon hence drifts sideways. That is the end of the color joint examination 2025. See you for the paper 2 discussion.